We have understood that if we change the magnetic flux linked with a given region, and if there is a coil in that region, some kind of EMF is induced in that coil, and that causes a current. So we understand that a time changing magnetic flux is causing a current to be induced. We can write this mathematically in the form d phi b by dt, which is the rate of change of the flux phi b, is proportional to the rate of change of current. If you are dealing with a solenoid, a coil in which the turns are very closely packed and there are n number of turns, we can say that the same flux phi b is linking with all of these turns uniformly. So the total linked flux with this particular coil can be given as n multiplied by phi b, and this is proportional to the current. So we see that this is a proportional relationship. We need an exact relationship. So I need some kind of constant of proportionality here. So what is this constant of proportionality? This is what we call inductance. And we are going to understand this effect, inductance, in terms of two coils placed inside each other. So this will be a case where the inductance of these two coils is linked to each other. This is what we call mutual inductance. Let's see how this works. So we have an arrangement here where there are two coils and one is nested inside the other, and in such a way that their axes are the same. So they have the same center, they are concentric. So we have an outer coil S2 with the radius R2, which is the larger coil with a larger diameter, and we have a smaller coil inside it with radius R1. Now there are a given number of turns per unit length. So let's say that for coil 1 or the inner coil S1, the number of turns per unit length is N1, and for coil 2 the number of turns per unit is N2. If you multiply these numbers with the length of the coil, you will get the total number of turns N1 and N2. We will see how we will use these numbers later. Now in this particular case, let's say that we have a current. We have a current I2 flowing through the outer coil S2. This current will generate a magnetic field, and because of the magnetic field there will be a flux, and this flux will link with the smaller coil S1 inside coil S2. The question is, how do we determine how much of the flux caused by coil S2 is linking with coil S1? We are going to make certain simplifying assumptions here. One assumption is that both of these coils are very, very long in comparison to their radius. This means that we are not really concerned with any flux leaking out of the edges, and we can also make the approximate assumption that there is no flux outside the physical limit of these coils. All the flux is confined to the region within these coils. This makes our analysis much more easier. Here we have a flux that is being linked with the inner coil. We can write this as N1 phi 1. That is the total flux linking with the inner coil. This is equal to M12 I2. So due to the current I2 in the outer larger coil, there is a magnetic field, and due to that field there is a flux. That flux is being linked with the inner coil, and how much of the flux is getting linked with the inner coil depends on the mutual inductance of these coils, or more accurately, the mutual inductance of coil 1 or S1 with coil 2. So that is what we have here in the form of M12. M12 is the mutual inductance of coil 1 with respect to coil 2. There is another way to find out what is the total flux being generated by coil S2, as all this flux is getting linked with coil S1. So What is flux exactly? Flux is the field strength of the magnetic field in a given region multiplied with the number of turns and multiplied by the cross-section area. So the cross-section that we will consider here is that of the smaller conductor. So that will be equal to pi r1 squared. This has to be multiplied by the total number of turns of the smaller conductor. That will be equal to N1 multiplied by L. And this in turn will be multiplied by the field generated by the larger conductor due to the current I2, which is given by the relation mu naught N2 I2, where mu naught is the permeability of free space, N2 is the number of turns per unit length for coil S2, and I2 is the current flowing through the outer coil S2. So if we multiply all of them, we get the expression N1 L pi R1 square mu naught N2 I2. Now, this is not a very elegant way of stating this, so let's make this a little more systematic. We can rewrite this as mu naught N1 N2 R1 square L I2. That looks better. So this is the total flux generated by the coil S2, which is getting linked with the coil S1. So this is equal to N1 phi 1. This is also equal to M12 I2. So we can equate this equation and rewrite this relationship as N1 phi 1 is equal to mu naught N1 N2 pi R1 square L I2. Now this is equal to M12 I2. So here we see that I2 is common to both these sides. We can cancel that out, which gives us M12 is equal to mu naught N1 N2 pi R1 square L. So this gives us the mutual inductance of coil S1 with relation to coil S2. Mutual inductance is not a set quantity. It is not only dependent on the properties of the material. It is dependent also on the size of the coil and the physical orientation in which the two coils are kept. This is a relatively simple analysis because we are making a lot of assumptions, but the inductance between the two coils can vary if the distance between them, if their relative orientation with respect to each other is changed. So this is important to remember that M12 is only true for this particular arrangement of coils. We can also ask another question. What is the mutual inductance of coil S2 with respect to coil S1? We can calculate that based on this relationship. N2 phi 2 is equal to M21 I1. We can perform the same analysis again. We can calculate the total flux that is linking with the coil S2. Please remember that these coils are very long, so their length is much greater in comparison to their radius. So we can make an approximation that the flux generated due to the current I1 inside the inner coil S1 is confined inside the cross-section of the smaller coil. So in this case, we can say that the total flux that is linking with coil S2 due to a current in coil S1 is equal to N2L multiplied by, again, pi R1 square, not R2 square, because we are still considering the flux to be confined inside the smaller coil, multiplied by mu naught N1 I1. So here mu naught N1 I1 is the magnetic field strength due to the current I1 inside the inner coil S1. So again, if you look at this equation, we can equate this to M21 I1, and this gives us the same equation as before, mu naught N1 N2 L pi R1 square I1. We can again cancel out I1. This again gives us M21 is equal to mu naught N1 N2 pi R1 square L. You will notice in this case that M12 and M21 are exactly equal to each other. So in this very simple arrangement, we see that the mutual inductance of these two coils with relation to each other is identical. Please note that most arrangements are not this simple, so mutual inductance will depend on the actual conformation, on the actual configuration of these coils.
Manorama Horizon, learning made simple.